Okay. Last time I started, what did I do last time? I started looking at the different switching techniques, right? PWM, PFM in DC to DC converters. That's mainly where we that's mainly one application, one major applications that requires magnetics, right? DC to DC converters, power supplies, and all of those. But in general, power electronics is one of the big field that requires to use magnetic components. So I started talking about different topologies, I believe, or not different topologies, but ways of selecting topologies, right? DC to DC converter topologies. And then I mentioned about the different switching techniques, PWM, PFM, and then I went over what else? I went over the different. I went over the inductor current, I believe, right? The shape of the inductor current in DC to DC converter, the way it looks, and then different operating mode. Continuous conduction mode, discontinuous conduction mode, and boundary conduction mode, right? And then I derived the general equations for finding the critical inductance, and then also the peak value of the inductor current. And then I believe I started a little bit on buck converter, and I'll continue that. But in the meantime, I'm going to skip ahead and go to this page right here. So if you please do that, if you have the book with you, page 147. I want to make sure that I finish this chapter today. And this is toward the end of the chapter. The discussion on the different topologies, there are a lot of them are just repetitions. That's why I could just save it after I do this, right? Okay, so this last part of the chapter talks about nonlinear inductor model, right? And you've done it in the lab this week, right? That in order for us to be able to simulate close to real world inductors, we need to incorporate nonlinear models for the inductors, right? So you cannot just do the regular or the standard model that you usually use when you use LT spice. So you usually just grab L, right, the L component, and you put it into the circuit, and that will be the end of it. Well, that L that you use, the inductance or the inductor model that you use in the past, right, typically what you use in the past, that model is a linear model, meaning that that inductor will never be saturated, right? It doesn't matter how much current you put in through that inductor, it will not be saturated, right? So that's not really a real world model, right? But it's good still to use for initial design. Right? Once you have the initial design working, then you can always start looking into how to design the magnetics, right? So you would first make sure that the overall DC to DC converter works, right? With all this linear model of the components. Once the DC to DC converter works, then you start looking into different components and change the model of each component into a more realistic or more real world type of model. So for inductor, right, there are two nonlinear models in LT Spice. You did one, right, one of them this week. Right? The first one is behavioral inductance specified with an expression for the flux. So it's basically a flux model, right? That's the first model. You didn't do this week. You did the second one. Yeah. What you did in the lab today and on Tuesday is that you change the L value with hysteretic core model, right? Based on a model first proposed by John Chan back in 1991. Okay, so that's the model that you use in the lab this week. Model one, let's go over the first model, behavioral inductance. The inductor current is referred to by the keyword X. So the letter X, if you put it into the L value, right, then LT Spice will take it as the current through the inductor, right? So the keyword X in the expression that refers to the inductor current. So it only concerns with saturation current value I set. So that's the model is, right? Only concerned with saturation current, nothing else. So you just need to identify what is the saturation current of this inductor. That will be the end of this model, right? The model goes like this. So you would put flux. So you would actually put this statement right here. So when you have when you pull in the inductor component, not inductance, inductor component into LT spice schematic, right? And then the L value, you right click on the L value, and instead of putting 10 microhenries or 100 microhenries, what have you, go ahead and type in this, right? And of course, you have to change these into numerical values, but this is the syntax, maybe, right? The syntax for this model. Right? So, for example, if let's say that you want the inductance to be 1 millihenries and it saturates at 4 amps, that's all you care about, right? Saturation, right? And in many cases, yeah, that's the only thing you care about, just the saturation. Then you could modify, right? Instead of putting L equals to 1 millihenry, you type this statement right there, right? Right click on L on the inductor and type this statement right there, right? Flux is equal to 1 milli, corresponding to 1 millihenries, right there. And then 4 corresponding to the 4 amp saturation current. Hyperbolic tangent of X, remember what X is, right? That's the current through the inductor at any given time. When you do the simulation, you'll take that value and place it into here, divided by 4, which is the saturation current again, right? So that's it, very simple, right? It's very simple. It's a very simple model. Again, only if you care about saturation current. Okay? So keep in mind that you have that model. The second model is a more comprehensive, right? More complex, more comprehensive model. Hysteretic core model defines the hysteresis loop with only 3 parameters. Right? So now with this model, you want the behavior of the core as you are applying voltage and then injecting current to this inductor to follow a certain BH curve, that BH curve that you've seen so many times, right? So it follows this curve. Okay. Of course, initially it'll follow. Initially, it will follow. Let me see if I can draw the straight line. When you first start the power, right? First run the simulation at the beginning. Initially, it will start from that point right there, and then once it goes back and forth, it will follow this curve, right? And it depends on the topology, right? Some topology only covers one quadrant. Some other topologies cover 4 quadrants. That's what we're going to talk about next. So, but keep in mind that you also have a more complex model for inductor in LT spice. It's called hysteretic core model. So it defines the hysteresis loop with only 3 parameters. And then H of C, the first parameter that we need to define is the coercive force, H of C, and then V of R, which is the remnant flux, not remnant, but remnant flux. And then V of S is the saturation flux density. And then the function, right? We have this hysteresis curve, right? We have, oh, you know what? I think I have a picture of this. That right there, right there. That's better. This one right here. Right, so it's going to follow this, and those are the 3 parameters that I just talked about. V of S is that point right there, so that's what you're defining. V of R, that's what you're defining right there, that point, and H of C. So as you are entering those numerical values, right, keep in mind that those values define those points, right? Or typically what we do is the opposite, right? You look at the data sheet, right, and look at the BH curve given in the data sheet, and then you find those points. Then you put those points from the data sheet into that model, into that parameters, right? V of S, V of R, and H of C. Okay. Now, when you first start the power, let's say that this is part of the inductor in the buck converter. At the beginning of the simulation, it will follow, from 0, of course, right? Something like that, right? And then it will start going back and forth, depending on the topology, right? Okay. And oh, yeah, I was going to say, this BH curve consists of two functions, right? The up and down, right? The up is right here, up and down, right? And up and down. So it consists of two functions. So the up function is right here, right? It's given in terms of those parameters, right? B of S, B of R, right? And then H of C. And then the B down, which is a function of H, right? Which is a function of current. As you know, H is equal to Ni over L, right? It's a function of the same thing, H of C, B of S, and B of R. Okay. Again, keeping in mind that H in here, as you know, that's a function of current, the mean path length of the inductor, and the number of turns, right? There you go. It's Ni over L. Okay. And if the inductor has an air gap, then you need to also specify that, right? Because that's going to be part of the mean path length. So with, or this is all N, or not or, just N. Where's my? So the mean path length with or without LG, which is the air gap. Okay. Okay. So those are the parameters that you need to put in, right? Right there, H of C, B of R, B of S, and then N, and then LM, and then LG. What about I? Well, I is the one that you're simulating, right? So as you are simulating the circuit, LT-Spice will grab that current, right, and then put it into the function here and generate this, follow this behavior right here. So the following BH curve represents these functions. B of S is the B-axis intersection, as I said earlier, right? Those are the points. I won't go through that anymore. But keep in mind, those are what you're defining. Okay? Again, typically you get these from the manufacturer's data sheet. That's what I said earlier too. The initial magnetization curve, the initial point is going to be halfway, right, between the two. So you could imagine, depending on the direction, it could be positive, it could be negative. That's going to be halfway between the two curves, like something like that. That's pretty good, actually. Right? So that's half of B up plus B down. Okay. Now that's what I talked about earlier as well, right? In addition to B of S, B of R, what is it again? H of C, yeah. B of S, B of R, H of C. When you look at the function, right? This function is in terms of H, right? And that H is a function of N, I, LM, and LG. So those are the ones that we need in the equation as well. But in terms of predefining the parameters, you only predefine N, L, and LG, not I, right? I is the one that you get from the simulation. So that's why I said right here, you need others. Oh, you have A as well, I forgot. The cross-sectional area, that's right. That's for the mu H, right? Mu H is equal to B, isn't it? And then B is equal to density, right? Flux density. So yeah, you're gonna need A as well. I forgot about that one. So you're gonna have to specify all of these. And where do we get these numbers? That's from your design, right? You select a core. When you select a core, then you're gonna get the A value, right? And then you're gonna get the magnetic length of the core once you select the core. And then you're gonna get the B of S, B of R, and H of C, right? Once you select the core, right? And then the air gap, or not just air gap, sorry, just the gap right there, that's from the design, right? And once you design based on the equation that we have in this book, for example, that we'll learn, following weeks, then you're gonna determine, okay, this is how much gap I need for this inductor or for this transformer, right? So this is from the design, right? Same thing with N, right? You determine that after you go through the equations, the design equations for building the inductor, okay? So in total, you have how many? 7, looks like here. 1, 2, 3, 4, 5, 6, 7. 7 different parameters that you need to put in order for you to be able to make use of this model, hysteretic model. Okay. Any questions on this? So you have the simplest model, right? In LT-SPICE, you have 2 different models: the simplest one and the more complex model. The simplest one only cares about saturation. Of saturation current of the inductor, whereas the second one is really, it's a really good model, because then you make use of the BH curve of the core. All right. Are there any questions? If not, let's look at some examples here. Applying these models. Now I have this linear model. I have a boost converter, first of all, right? There's a boost converter. How do I know this? Because the input side has inductor, on the output side has the diode, and the switch is inside the controller. Right? This is an example of a PWM controller, right? And this is using a linear model. This is what you usually use, right? When you using inductor in LT-SPICE, just linear model, not going to saturate at all. It doesn't matter how much current you put into this inductor, it's not going to saturate. So for this example with this load right here, right, you can see that the inductor current looks like a triangular waveform, as I discussed last time, right? Inductor charges, discharges, right? Charges, discharges, right? So triangle. Okay, so that's what we usually have. And then I am changing the model now to the first model, the flux model. So rather than putting, what did I put earlier? 150 micro, now I put the flux model in addition to the 150 micro, right? So I put in the saturation amperage, which is 1.2768. Not sure why I picked that, but just for the sake of example, there's the saturation current right there, 1.2768, right? And then you can see that for this one, you kind of see a little bit, right? I don't know, it looks like a little bit distorted around here. It's not quite a triangle, but maybe you could see a little bit there. It's kind of curvy, right? Right there. It's kind of curvy right there. So that means, it is not a linear model anymore, right? It's not a perfect triangular waveform anymore, right? Okay. And then here I'm using the second model, but in this case, it's not saturated. So I define all of those, 7 parameters. See that? Number of turns is 50, right? Air gap, and then mean path length, right there. And then the cross-sectional area of the core, saturation flux density, remnant flux density, and then coercive flux right there, coercive magnetic field intensity, right? The same load, 24 ohms, and you can see if I set up the core to be this way, so this is basically one core that I use, right? If I use this core, right, then and that design with 50 turns, then you can see that it is not saturated, right? It's a perfect triangle, just like before. So this one is not saturated. But when I change, if you look at, if you compare the saturation region, right, from before, right, before, what do I have here? The saturation region I have is 0.4, 0.75, 15.4.75. Oops. Here I still have 15, but instead of 0.4 and 0.5, now I am reducing the saturation point. I am decreasing the saturation point. So it's easier to saturate this inductor now, right? Because these points are lower. I'll go back to this the edge curve right here. Where is it? Okay, here, these points now are lower, right? Say over here now. So now it's easier to saturate this core, right? So that's what I did. Basically, this implies that I'm using a different core. So if I'm using a different core, then it will have different saturation points. And for the same load, 24, look at what happened. Now I'm saturating the inductor. Okay, and you can see the peak, maybe that it is 1.6. You can actually see the peak value there, 1.6 compared to before 1.48. See that? So for the same amount of power, output power, right? Different cores will give you different inductor current, right? In this case, you are saturating the inductor if you are using this particular core. Okay, even though I didn't change the wattage or the output power. Is that it for this one? Yes. Any questions on this? And ORCAD PSpice has the same thing. The thing is, I've not got a chance to look into or put together the notes for ORCAD. If I get the time, this weekend, I will do that. I'll share it with you. But yeah, I think it's also good to know how you model inductor with nonlinear characteristic or nonlinear behavior in ORCAD PSpice. Okay. Any questions? If not, let's go back to the buck converter discussion. That's going to be a lot of repetitions here, so I'm going to go slowly first and then go faster afterward. Okay, we'll talk about this last time, right? Yeah, all right, that's it. We've done that. Where's buck? Yeah, there's the equation, just to summarize what we did last time as well. We derived the equation for the critical inductance, right? You can use the on time or the off time, right? Sorry, yeah, either this one or this one. Oh, wait, no, not that one. This is already buck converter. No.
It was page 120.
Page 120. Oh, thank you. Oh, page 120. Okay, yeah. So this is the general equation for transfer function. Okay, there's the buck converter. Okay, thank you. So what we did was we derived the transfer function first, right, using volt-second balance, right? As you can see, it's not really bad, right? You just apply volt-second balance and you get the transfer function, and then now you could also derive the critical inductance, which is important in DC to DC converter design or power supply design. You need to know the critical inductance. Why is it important? Because that would determine the operation of the converter, right? Whether it be operating in continuous conduction mode or discontinuous conduction mode. And why is it important to know whether or not the converter is operating in CCM or DCM? Okay, because that is going to affect the transfer function right there, right? I mentioned last time that this transfer function is valid only for CCM, and assuming ideal and steady state. So if you'd like the converter that you're designing to follow this transfer function, that V out is going to be equal to duty cycle times V in, then you want to make sure, you want to guarantee that, you want to ensure that the converter is always operating in CCM, right? But as we know, as we learned from our last class, that that's not possible, that we can always it is not possible to always maintain converter in CCM, right? Especially at low power, right? Because then eventually it will reach boundary conduction mode, right? Let me just go back to that picture. I have that picture somewhere. Yeah, right here, right? So per given inductance value, right? Any inductance value, right? It is impossible for us to be able to maintain CCM throughout, the current from 0 amps to the maximum amperage, right? It's going to be impossible because this inductor current has delta IL, right? So eventually, right, because this current has delta IL, eventually, if you are decreasing the output power, this inductor current will decrease, will shift down and down and down until eventually, when the current is low enough, the minimum value of this inductor current will touch 0, right? At which point we call this BCM, right? And if you keep decreasing the current output power, then you get the DCM mode, right? Okay. So it is impossible, but then it is possible for us to limit the operation of the converter such that, throughout a certain range of output current or output power, the circuit is operating in in CCM mode. And below that current, we don't really care much about the operation in terms of transfer function of the circuit. Okay, so therefore the defining factor here would be this current right there, right, for critical inductance, right, BCM mode, and we talked about it last time. And this translates into, so from the BCM condition, it translates into what? Into critical inductance, right? So if we can find the value of critical inductance at that condition, at boundary conduction mode, then if we pick our inductor value to be larger than the critical inductance, then we are guaranteeing that that our converter will always operate in CCM at the given BCM condition, right? Okay. So let's go back to here. So the critical inductance, you can find a value by using on time or off time. If it's on time, then you use VL on times duty cycle divided by 2 times IL average FS, right? And we learned that for buck converter, VL on, voltage across the inductor when the switch is on, is equal to V in minus V out, right? Times duty cycle. And then IL here, right? So this is what makes different topology unique, is the IL value. The IL average value would depend on the topology. It's topology dependent. Right? For a buck converter, you can see that IL average right here. This is our IL. The average value of IL must equal to the average value of I out. Right? For those of you who took 410, you already know this, right? By KCL at that node, I know that IL of T is equal to IC of T plus I out of T, right? But if you take average value of this, the average value of IL should be equal to the average value of capacitor current plus the average value of the output current, right? And we know from circuit class that the average value going through the capacitor must be equal to 0, right? Because capacitor looks like an open to DC. So therefore, the average value of current in a buck converter, average value of the inductor current in a buck converter should be equal to the average value of the output current. And that's going to be different if you have a different topology, right? That IL value. So here, I replace IL with I out, right? As you can see from here, I replace IL with I out. So now you know the reason, okay? So that's the equation to find critical inductance for buck converter. Here's an example. A buck converter has an input voltage of 48 volts and average nominal output voltage of 12 volts. determine the transfer function and the critical inductance if the switching frequency is 200 kilohertz. Rated output power 100 watts, and CCM must be maintained down to 20% radiate load. So this 20% is what we define. This is how we define BCM, right? So 20%. Remember, we keep decreasing current, the output power, until the minimum inductor current touches 0, right? So for this example, that condition refers to 20% of the I out max, right? And I out is equal to P out divided by V out, right? P out max divided by P out. And what is our P out max here? 100 watts right there, right? So 100 watts divided by V out is 12, whatever that is, right? So so 20% of this, oh, sorry, how do I do this? The 20% of this corresponds to 20% of 100 divided by 12. I should put this whole thing is equal to this. Just the I out max is equal to that, right? So that 20% is very important to know, okay? Again, people who took EE433, they already learned this, but for those of you who have not EE433, that 20% is a really crucial information to have, because that defines our BCM, which then defines LC, critical inductance, right? So BCM is 20% of I out max in this case, right? And I use MATCAD to do this, right? I define all of those given values, find the duty cycle, and then just type in the equation for LC, and I get the critical inductance. See that right here? Ooh, did I mess up on this? Oh, no, it's not. Okay, it's not. I thought that's supposed to be 20. That's just the part of the equation, right? There's a constant 2 right there. The 20 is actually right there. Percent CCM should be 20 right there. Whew, I thought I messed up. All right, so 2 times percent CCM, which is 20% of the max output current, as I explained earlier. So that gives you the critical inductance, 13.5 micro, right? So in practice, of course, you then will pick the inductor value, right? The inductance of the inductor value to be larger than LC, larger than this value, right? But for this example, just for the sake of example, I'm going to use the same inductance to determine delta IL. Again, in practice, you would choose inductor value to be larger than the critical value, and then use that chosen inductor to get the actual delta IL. Okay, but here I'm just going to use I'm just going to do this. L is equal to LC, right? And use that LC into calculating delta IL right there. That gives us 3.33 amps, right? So what that means is that at boundary conduction mode, right, delta IL right there is 3.33 amps. That's what it means. Okay. Because again, we calculate delta IL on the critical value, right? That's BCM, isn't it? So make sure that you understand the physical implementation, physical implication of what these numbers are, not just for the sake of calculation and numbers, but understand what goes on, how this affects the operation in the circuit. So in this case, if you use this inductance value, L equals to LC, then peak-to-peak inductor current will be 3.3 amps, right? And then the peak of the inductor current should be equal to I out max plus delta IL over 2. So this happens at the worst case scenario, right? The other end, the other extreme. If you keep increasing the output current, then this triangle waveform, this is IL, by the way, right? This IL is going to go up, right? It's going to shift up until it stops at the maximum output power, right there, right? That corresponds to output current if you divide by V out, right? And then we need to know this peak point right there, because that is related to the I sat, Remember ISAT model that I talked about earlier for LT spice, right? So if that is what you're concerned, right, then you need to find that, you need to calculate that ISAT from here, right? So that's this right here, right? IL peak. So IL peak is equal to P out max over V out. That's maximum output current, right? Output current at maximum output power plus delta IL divided by 2. That happens to be 10 amps, right? So if I were you, if I were to choose the inductor for this example, I would choose L value that is larger than LC, and ISAT of the inductor that's going to be larger than 10 amps. Any question on this? Okay, so I need to emphasize again that out of this class, when you select an inductor, not only that you need to pick the L value, but now you know that you also have to pick ISAT, right? And these are given when you buy an inductor that will give you this value, this rating for ISAT. Any questions on this? Okay, when it comes to the BH curve, right? So here's the BH, the major loop of the core. If you were to excite the core with AC signal at certain frequency, right? But in this case, we are not doing that, right? We are not exciting the inductor core with AC voltage, right? It's just with AC current. It's just DC, right? This current right there is always positive. It's always above 0, right? So therefore, the minor loop, right? That's the minor loop right there. Will be going back and forth in the quadrant 1 of the major loop. So we have the major loop, right? That is provided by manufacturers, right? But when you operate the core, you're only operating the core on this portion of the major loop, right? Okay. Hopefully that makes sense. And if you look at the 2 points, these are the 2 critical points, right? That point right there and that point right here, right? This point on the left, right there, that corresponds to IL min. Right? And then the one on the right side, that's IL max, right? Because if you project that point to the x-axis, the one on the left, that corresponds to this H right there. Right? So that's H min, and on the right side, on that right point right there, right, that is projected to this point right there. That is H max, right, corresponding to IL max. So H min corresponds to IL min, H max corresponds to IL max, right? And then the difference between the 2 points should correspond to delta IL, right? So from here to here should be the delta IL. All right. Any question on that? Okay. And if you are operating I'm going to erase this, okay, because it gets crowded here. If you are operating this circuit in continuous conduction mode, then the IL min should be above 0, right? Just like this picture shows you. So this minor loop that you see in front of you, that represents the operation of the buck converter in CCM. How do I know that? Well, because the IL min point is not at 0. It's not here. It's not touching. It's not touching the y-axis, right? Make sense? Now, what if we operate this buck converter in DCM? Then it's going to look something like this. You see that? So the same area, the same minor loop, except now it's shifted down until the IL min point, which corresponds to H min, touches 0 right there. So I know that this is an example where we have DCM operation. Is that clear, hopefully? So the same delta IL, you see the swing is the same, right? The same delta IL. but now it's shifted down because we are we're injecting less current, right? So that's why the minor loop is shifted downward until the minimum touches 0. Okay. What if I keep increasing the current from here? What if I keep increasing the current? Well, this will be traveling even higher and higher, right, for the same area, right? The same area. And so here, if I put it on higher position of a major loop, that's going to be about the same area right there, right? It's going to be like that. And then what if I keep increasing the current even more? Then for the same area, if let's say I increase the current to this point, you can see that in order to have the same area, then it has to go all the way to saturation region right there. I don't know if that's the same area or not, but assume that they're the same area. So it's pushing the H, right, which corresponds to IL max, right, to the saturation point. So now look at the swing. It's big, right? Delta IL now is big. That's why in the LT spice discussion that we had earlier, current looks like this. Oh, sorry. Instead of triangle, current now looks like this, right? Something like that. Right? It's no longer triangular waveform. Okay. Any questions on that? Okay. If not, then let's move on to boost converter. Excuse me. For boost converter, we have inductor at the input, right? Switch in the middle and diode at the output. So what's going to make the difference is the VL on and VL off, right there, right? And we need this for transfer function, and we also need this for calculating the critical inductance, right? So what is VL on? VL on is voltage across the inductor when the switch is on, right? So when the switch is on right here, what is voltage across the inductor? That's equal to V in, right? And when the switch is on, this diode is off. Excuse me. So the diode is off. So now we have voltage across the inductor equals to V in, and then when the switch is off, so VL on is equal to V in. When the switch is off, diode is on. It's a short, right? So if this is off, diode is on. So this is a short. So now voltage across the inductor must be equal to V in minus V out, right? Because that now this node is the same as that node. Okay.
Professor?
Yeah.
So just for estimation purposes, we're ignoring the voltage across the diodes.
Yeah, these are all ideal. Okay?
Oh,
these are all ideal components.
Okay, thank you.
Yeah. And then I have some explanation on the boost here in terms of the property of the boost. So boost means that output voltage is larger than the input voltage. And then, hang on a second. And then input current is inherently smooth and output current is choppy, right? Because we have a diode that turns on and on. So very good input current characteristics. Basically, the input current is going to be close to DC, right? Or mimicking DC, triangular waveform. Whereas the output current is going to be choppy. It's going to be on and off, on and off, on and off because of the diode. So bad output current characteristics. All right, so that right there. Now that I know VL on, VL off, now I'm ready to derive the transfer function, right? Same thing, same as buck, right? What is the volt-second balance for buck boost and buck boost? That's going to be VL on times D plus VL off 1 minus D equals to 0. That's it. And we already know what VL on is, right? That's V in, and VL off, that's going to be V in minus V out. And then the rest is going to be just algebra. At the end, you get the transfer function for a boost converter to be equal to V out equals to 1 over 1 minus d times b in, or b out over b in equal to 1 over 1 minus d. Okay. The same equation that you apply for critical inductance, right? VL on over d to IL average times switching frequency if you're using on. And we already know what VL on is, right? VL on is equal to V in, right there. VL on is equal to V in. Right? Just plug it into that equation for boost. And IL average now is going to be different, right? You can see that for a boost converter, where is IL? Where IL is at the input. In a buck, IL is at the output. So therefore, for a boost, IL average must be equal to I in average, right? And I in average is equal to P in over V in, right? And if we assume ideal, no losses, no drops, no forward drops, no resistance, right? Then I know that P in must be equal to P out. So therefore, I in is equal to P out over P in. Okay? So that's what I would put in that equation right here, I believe. Yeah, right there, see that? So I in is equal to P out over V in. So IL average is equal to I in average is equal to P out over V in. So then the critical inductance equation now becomes this equation right there. V in cancels. Oh no, actually not cancels. V in becomes V in square, right? Because then it goes up to the numerator. So here's the equation for critical inductance for boost converter, right? Keep in mind that P out is going to be calculated at BCM, not max, but at BCM. Okay. Here's an example. Boost converter has input voltage of 24 volts, output 72 volts, and switching frequency 500 kilohertz. Output power, that's max, 50 watts. And again, see this, CCM must be maintained down to 25% of rated load current. So that defines the boundary conduction load, right? And yeah, same as before, it's asking for critical inductance and peak current, IL peak, right? Again, I use MATCAD, right? Given typing all the given values, and then find the duty cycle from the transfer function, right? My duty cycle there is 0.667 there for this example. And then the critical inductance, I just plug in check, right? We have the equation for critical inductance that we derive. And keep in mind that this P out has to be multiplied by the 20%. P out max times the 25%, sorry. That will give us the critical inductance. And I'm going to use this like in the buck example. I'm going to use this critical inductance to calculate delta IL right there. And delta IL is now equal to 2.604 amps. Oh, sorry, 1.042, wrong equation. So that's delta IL. That's peak-to-peak inductor current, okay? 1.042 amps. The peak value, which is important for us to know as well, because that would define IL sat of the inductor, that is again being calculated from max value, right? IL average, which is P out max over V in, plus delta IL divided by 2, that gives us 2.604 amps, okay? Peak value. So if I were to choose the inductor for this example, I will choose L to be larger than 30.72 microhenries, and IL peak, IL sat of the inductor to be larger than 2.604 amps. Any questions on this? The minor BH loops for a boost is exactly the same as the buck converter. So I won't go through that anymore. It's always it's only one quadrant, so it looks exactly the same. CCM and DCM exactly the same as buck. And then this third one, I'm going to go through this quickly. Buck boost converter, right? That's another basic converter. And there's the ground right there, which I didn't draw. Right? This is a converter where the output could be either higher or lower than the input. right? But the output is going to be inverted from the input based with respect to the input. So if the input is positive, the output is going to be negative. Okay. And this is a converter that has bad input current characteristic as well as bad output current characteristics, right? If you look at the input current, it's going to be choppy, right? Because why? Because it is connected in series with a switch, and we know that switch turns on and off, on and off, on and off, right? So you're going to have a choppy, discontinuous current at the input, which is far away from DC. Remember, DC is continuous, right? Flat, right? DC is flat. This is no way going to be flat, right? It's going to be on and off. Same thing with the output, right? The output is supposed to be DC as well, right? Flat. But what we get is that it's not going to be flat. Why not? Because we have a diode at the output. A diode is another switch. It'll turn on and off, on and off, on and off. So there's no way that we have a continuous output current in the buck boost, right? So in spite of the fact that buck boost can give us either higher or lower output voltage than the input, this converter is pretty it's not really good when it comes to power quality at the input and output, because they has bad choppy currents at the input and discontinuous current at the output. Okay, bad. Physically, it just means that you're going to need heavy filtering at the input and output, right? So that means cost, right? And yeah, the name buck boost comes from the fact that it is a combination of buck and boost, right? If you remember, buck looks like this, and boost looks like this, right? So look at the input of a buck. This is buck, right? And this is boost. Look at the input of a buck. So it's a, what do you call it? It's a switch, right? That's what you see here. So the input stage looks like a buck. Look at the output stage. Look at the output stage of a boost. It's a diode. Look at the output stage of the buck boost. It's a diode. So that looks like a boost, right? That's why it's called buck boost, because it's combining buck and boost. Unfortunately, when you're combining buck and boost, you end up with bad input current characteristics and bad current output characteristics, right? And in EE433, we talk about how to improve this instead of combining buck and boost. Why not combining boost and buck, right? So if the input is a boost input, look, the input of a boost is inductor. That's going to be good input current characteristic, right? Because you have inductor at the input. And then buck, look at a buck output, it's also inductor, right? So rather than buck boost, we should have boost buck. And for those who took EE433, what do you call that topology? Boost buck, come on. I know I have several people here who took EE433.
Juke?
Yeah, not Juke. Juke. Okay, Juke converter. Very good. Okay, anyhow, I'm not going to go through these in details, but same thing, right? You do the transfer function with volt second balance, right? VL on, D on, actually no, VL on D plus VL off 1 minus D, because the T cancels anyways, right? And then you just need to know VL on and VL off, right? And VL on, if you look at buck boost, what happens when the switch is on? What is the voltage across the inductor when the switch is on? When the switch is on, diode is off. And you can see that voltage across the inductor is equal to V in, right? That's when the switch is on. When the switch is off, diode is on. And if diode is on, switch is off, look at the voltage across the inductor. It's exactly V out, right? So that's what you have for a buck boost. This is going to be equals to V in. That's going to be equal to V out. Okay, and then if you do the algebra, you get this equation for the transfer function. Right there. Okay. Minor loop's going to be the same as before, so I won't go through that. Okay, next is flyback. Right, so now we go into the isolated topology. Right? Flyback is being derived from buck-boost converter, right? So if I draw a buck-boost converter, wrong, no, okay. If I draw a buck-boost converter, like this, right? That's a buck-boost. A flyback would be derived from this topology. How so? By replacing the inductor with a transformer. So now you replace the inductor with a transformer, and now you have a flyback there. Okay, so that's basically a isolated buck boost, right? Remember, isolated means you have a transformer. There is a transformer in the converter. So if you replace the inductor with a transformer in the buck boost, then you get a flyback right there. Okay? And just like a buck boost, it will have bad input current, output current characteristics, right? Input's going to be discontinuous because you have a switch right there. Output is also going to be, output current is going to be bad as well because it's discontinuous current because of the diode. Anyhow, you can see that in flyback, there is no inductor, right? There is only a transformer. So the way we derive the transfer function is by looking at the magnetizing inductance of this transformer, right? You probably remember from EE433 that if you have a transformer, then real world transformer will have the following model, right? Like this. Oops. Right there. Right? There. Okay, so then for the flyback converter, right, we are going to use this magnetizing inductance to derive the transfer function. Because, you know, remember, this is a energy storage component, right? And magnetizing inductance are the one that is going to be in parallel with the input, right? It's going to be in parallel with the input. So that's the inductor that's going to store the energy, right, for this transformer. So imagine you have what you're seeing here, that's just the ideal portion. That's just this portion right here, right? But within this transformer, we have magnetizing. I use a different color. We have a LM, magnetizing inductance, which is in parallel with the windings, right? As you can see from here, this magnetizing inductance right there is in parallel with the windings. So that's how I draw that right there, okay? So then when the switch is on, what happens when the switch is on? When the switch is on, the diode is off, right? So then voltage across the magnetizing inductance, again, assuming everything's ideal, okay? Everything, all components are ideal, no losses, no drops, right? So the switch is ideal as well. When it's on, there is no drop across the switch. So therefore, when the switch is on, diode is off, voltage across this magnetizing inductance is exactly equal to V in. So VL on, VLM on is equal to V in. Okay. All right. What about when the switch is off? When the switch is off, I have it right here. Okay. VLM on is V in. When the switch is off, right there, right, the energy that is being stored in the magnetizing inductance has to be released, right? So it's looking for a path to release its energy, right? And by doing so, it will flip its voltage, and that in turn will turn on that diode, right? So the diode now turns on because now it's forward bias, and now that inductor, the inductance that we have here, is now appearing on the secondary side, right? now appears on the secondary side and is discharging its energy that way. Okay. All right. So then now we should be able to get the voltage across that magnetizing inductance, right? Because that is just V out. See that? VLM here is equal to V out. However, when you're deriving the transfer function, you have to derive it on the transformer. You have to derive it based on one side only, right? You cannot use the on time of the transfer function on the primary side and then the off time on the secondary side, right? So how do we deal with this? Well, we can just reflect back, right, the voltage across the inductor to the primary side, right? When we did the VLM on, right there, right, we measure this voltage. We calculate this voltage on the primary side, right? VLM on is equal to V in. When we do the VLM off, unfortunately, the inductor moves to the secondary side. And then we know that the voltage across that inductor now is V out, right? So then what do? Well, we just need to reflect that voltage across the inductor to the primary side. And you learn how to do that, right? In 212, right? You just multiply by the transfer function. Turns ratio, right? The turns ratio is n to 1 right there, okay? So when you reflect that back into the primary side, that voltage across magnetizing inductance during off time is minus V out times N. So that's what I put into the volt-second balance. The same volt-second balance, right? VLM on times duty cycle plus VLM off times 1 minus duty cycle equals to 0, right? And from there, it's just algebra. You get the equation for V out in terms of V in, okay, for flyback. All right, and then for the critical inductance, the same equation again, right, as before. The only thing here is that we know what VLM on is. That's just V in. But ILM average, that's the one that's kind of tricky. And I'm not deriving that here because I think that's going to be beyond the scope of this class. Again, if you're interested, you can take EE433, but it can be proven that ILM is equal to this equation right here, right? So yeah, so that's it. That's how you find the critical inductance, right? Right there, right? And keeping in mind that ILM is this equation right there. And here I'm just rewriting the equation. So there's several equations that you can use for finding critical capacitance, right? There's more equations, right, using different parameters. This one is using P out and V out. Okay. Now what I would like to show next is the minor loops of flyback. Now flyback transformer only uses one minor loop. Why is that? Well, because the current through the magnetizing inductor is always positive. We are not applying negative current through that magnetizing inductance. That's why it stays in. It stays in the quadrant 1. This is DCM, right? Operation, as you can tell from the curve, not from the curve, from the loop touching the 0, and this one is the CCM. Okay. Now, because of this, transformer used in flyback is not really utilized, to its full, not to its full capability. But what I'm trying to say is that flyback transformer is not utilized efficiently or effectively, I should say, effectively, right? The reason being is only using one quadrant. What do I mean by that? Okay. Take a look at, let's do the CCM. Let's look at CCM. Let's say that this is how we are operating the transformer right now, right? That's the minor loop right there, right? Depending on the delta IL of the magnetizing inductor current, right? Just like we discussed in Buck. Okay, for this operation, take a look at current, the maximum current that this inductor will see, or this transformer will see. That will be corresponding to this point right there, right? That's going to be proportional to IL max, right? And this is per given power, right? Per given output power, you get this area right there, right? So let's stick with the same output power. Let's say that this is operating the flyback transformer with that output power. That's the area, that's the minor loop. And for that output power, current max is right there, okay? Now imagine if I am able to use 4 quadrants rather than 1 quadrant. What do you think is going to happen? What's going to happen is this, right? If I'm able to use the transformer more effectively or more efficiently too, right? Then this area, if it's 4 quadrant, will be around here. I don't know if I can draw the same area, but you get my point, hopefully. So let's assume that's the same area. Right. Right. So if you shift this area down and down until it covers 4 quadrant, right? Then you can see that that it is making use of the transformer better, right? We utilize the transformer better that way. Why is that? Well, because for the same amount of power, look at the area, it's the same area. Current stays the same. Stays the same. It's not stays the same. Current is less now, right? It's less current. IL max, if this is number 1, this is number 2, then for the same output power, IL max 2 is less than IL max 1. Isn't that great? Right? For the same amount of power, to deliver the same amount of power, I require, or the core requires less current for the same amount of output power, if we're able to operate this core in 4 quadrants. Hopefully that makes sense, right? So that's why flyback and any other topology that has 1 quadrant, it's not really utilizing the transformer better, because we're basically wasting the core, right? Imagine if I'm able to operate these in 4 quadrant, then I don't need a core that has this BH curve, right? I can just buy a core, a smaller core that has a BH curve that cover this major loop like this, right? You agree with that? I don't need a big core. I just need a smaller core that has this major loop. That's the implication of this, right? Hopefully that makes sense. Any questions on this?
Yeah. If in the BH curve, if I'm in that negative quadrant, does that mean that I'm in the continuous conduction mode?
Yes, it is a continuous conduction mode, but then the core itself is seeing negative current, right? You'll see that it's just a matter of how we. Okay, this is actually flux, right? Not really current, it's flux. So the current is still positive, but that current, when it goes through the core, through the winding, produces negative flux. Okay.
Got it.
So I think we'll wait until you'll see the one that has 4 quadrants, so that you'll know.
Okay. Thank you.
Yeah. Okay. All right. Now I'm gonna just skip ahead to, because it's the same thing for that one, right? Just to answer Uriah, right? Is it the one who asked it earlier?
Yeah,
Yeah, let's look at push-pull, for example, right? You see here, when I turn on switch 1, for example, current flows through the first switch right there, right? So that current to that inductor is positive, right? Okay, and then if you look at the dotted terminals, right there on top, current goes into the dotted terminal, right? That's going to give us flux. That's going to go into one direction. Let's say that direction is from left to right, flux, right, inside the core. Okay, and then if I turn off S1, this is off now. I turn on S2, then what's going to happen? Then current now flows through here, right? Okay, through that inductor, that current is still positive, right? Because that's a separate inductor, see that? But the thing is that current leaves the dotted terminal, right? If the current leaves the dotted terminal, means that the flux that is being produced is the opposite direction, negative flux. So now you have positive flux and negative flux. So when you draw the BH curve of that, it's going to be something like this, right? It's going to be, the minor loop is going to be plus and minus that way. Does that make sense, hopefully?
Yeah, I just have another question.
Yeah.
Does that mean what mode is that operating in?
Well, we have in output inductor right there. So if you look at the output inductor, it's always positive. Current is always to the right. So that's still CCM. Okay.
Got it. Okay, thank you.
Yeah, so we have two magnetics here. We have the transformer and we have the inductor. If you look at the transformer, right, the flux inside the transformer goes up and down, positive, negative, positive, negative. The inductor on the output side, right, the flux is always positive, right, and the current is always positive as well. Okay.